So we have Regina Sarmiento, and she's going to tell us about capturing the physics of MaNGA galaxies with self-supervised machine learning. You have 12 minutes. I warn you at 3 and 1.
Great, thank you. Well, thanks for the introduction. I'll only add that I'm a PhD student at the Instituto de Astrofísica de Canarias. So, well, what we're trying to do here is try to trace galaxy evolutions through the specially resolved physical properties of the observed galaxies. And we're going to do this through a data-driven perspective. And we're going to use MaNGA data, which is, MaNGA is a survey that has integral field spectroscopic data for 10,000 nearby galaxies of all types. Now, ooh, sorry. Yeah. Okay. So this is a great data set, considering how expensive it is to get this data. However, it's a bit tricky to treat it as a whole, because we know that the galaxies have been observed with different number of fibers and different spatial coverage. So this is a very complex data set, not only because of its volume, but also because of these differences between the observations. So how can we easily explore this high-dimensional data set? In general, when dealing with large and complex data sets, what we would like to do is we would like to have a manageable number of parameters that are representative of our object of study, in our case, galaxies. So we want to perform a dimensionality reduction on one side, and that this excludes the noise present in the data. So we're going to work in particular with our raw data is going to be galaxy maps derived from the spectral cubes. And in particular, it's going to be the V-band reconstructed image, luminosity weighted age and metallicity, the radial velocity and velocity dispersion. So we want to go from this raw data space into a space of parameters that describe our galaxies. And there are different ways of doing this. In general, we want a function f that it could be a, something that we derive using our prior knowledge of the object of study. So for example, deriving single quantities from a determined group of pixels. Or we have another option b, that is extracting the dominant features of the data and see how this distribute. So the most standard way of doing this would be using principal component analysis, where you decompose your data into a few parameters that minimize a reconstruction error. Autoencoders would be the nonlinear extension of this. And, well, let's see how the simplest model works. So we get our data, we run it through the principal component analysis, and we obtain our principal components. Now, if we project these parameters that we obtain at the end with UMAP into a 2D space, so here the plots that I'm showing are not, the axes are not physical parameters, physical magnitudes, let's say, but rather represent the position of each galaxy in this parameter space. We can see that if we color code this, the galaxies according to a physical property, like it could be the age, then the organization of the galaxies is not obviously driven by the age, but because we see this like finger-like structures that cannot be explained by this parameter, but rather if we look at the number of 0 pixels that we have in each stack of maps of each galaxy, we can see that the correlation is quite strong. So what's happening here is that in the end, PCA is picking up the size of the IFU as a dominant feature, and that's something that we are not interested in finding. So we have to consider other options. So we're going to see what contrastive learning is, and to see that, we'll see how it's trained. So contrastive learning is an unsupervised algorithm to obtain representations. So if we have our training data set, which is a set of maps of galaxies, we duplicate them. Then we apply some transformations, like it could be zooming in or rotating the images. And then we run this through a neural network. Now, the neural network's weights are adjusted such that the representations that come out at the end, so the Zs, are pushed together if they come from the same base image and pulled away if they come from different images. So in the end, what you're trying to do is you're trying to make your model invariant to the transformations that you apply at the beginning and get a representation space that is organized according to similarity. So we applied this to our data set. We're going to, in particular, use this set of transformations, that it would be model variation, where we replace some maps with analogs obtained with a different pipeline, rotation, resizing when we rescale the size of the image, noise perturbation, where we vary the value of each pixel according to a normal distribution, and blurring, where we apply a Gaussian kernel. So we obtain a parameter space of 1,024 parameters, and we do the same as we did before, project this with UMAP to visualize what we are obtaining. So we can see that there is a soft transition of age from one side of the plot to the other side, meaning that the distribution of our galaxies in this space correlates with age. And this correlation, the correlation that we saw before with PCA with the number of 0 pixels, is not as obvious in this case. So this is good, this is what we want. And this happens with other parameters as well. On one hand, we have the physical parameters, so you can see that the soft transitions appear mostly for the contrastive learning, which is the SimCLR column. And for non-physical parameters, the distributions for the SimCLR are mostly random. So great, now we have our representation space where our galaxies are organized according to their physical properties rather than instrumental biases or so. But also this is a challenge because it's a quite high dimensional space and we need to interpret it. So what we proposed to do was to do a non-supervised classification to understand what are the mean properties of each group occupying the different regions of the representation space. Then there are other applications like outlier detection, similarity search, and then we're also moving towards comparing with simulations with this representation space. So in the clustering applications, what we did is just use the standard algorithm for clustering, like k-means, and separating into 3 groups, you can see that in this plot with mass and star formation rate, one of the clusters falls in the star forming main sequence. Then we have a group of high mass early type galaxies and another cluster that has low to intermediate mass quiescent galaxies. And if we look at the morphologies of these clusters, we can also see that, for example, the star forming galaxies have the latest types as we could have expected. So that's great. But now, well, this is analyzing the global properties, so meaning that we are keeping the relative values for each galaxy when we normalize. But when we look at the internal structure of the galaxies, so now we are normalizing each map such that it spans from the range from 0 to 1, we can see that we still find this division where we have one cluster that mainly contains the star-forming galaxies, and another cluster that doesn't occupy that region at all and has intermediate to high mass quenched galaxies. So meaning that this algorithm is allowing us to find the differences between these galaxies, only considering their structure, their internal structure. And, well, something that I'll add also is that, for example, in the first case, it's not new unknown classes. It's something that we already know. But it's great that we could find this in a completely unsupervised manner, only telling the networks what is what we don't want from the data. So for the outlier detection, what we would do is we would find or try to find the isolated representations or representations that appear to be at the edges of this representation space. And this is what a student that worked with us did. And she, from 10,000 galaxies, she went to a sample of 100 galaxies that one could actually look at. And she found really weird galaxies, so, well, that was working quite well. Then we could also perform similarity searches. So if we select a galaxy, and this would be the target galaxy that has those sets of maps, we project it to the representation space, then we look at the neighbors in the representation space, and if we go back to the maps, we obtain these galaxies that are close by. So this is a super interesting approach for to find galaxies that have the same structures, in particular mergers, which is the case. And then with the comparison with simulations, what we are basically doing is grabbing simulated galaxies, emulating the MaNGA observations, and then projecting into the representation space. So we can follow where these galaxies fall. On one hand, we're going to use a suite of snapshots of simulated merging galaxies. So we can see where they fall in the representation space through time and see how we can if we can accurately identify the different stages of the merger. And also because we know of a number of merging galaxies in the MaNGA survey, we can see if they're falling also in the same place and try to trace also new merging galaxies with a similarity search. And then the last would be the comparison with a cosmological model. So we're going to use TNG 50 simulated galaxies and observe them as MaNGA. Then we project them into the same representation space that we found before. And we can ask then, do they populate the same regions? And because we know the assembly history for the different galaxies in the TNG sample, we can see if the galaxies that fall in the same place, do they have the similar accretion histories? Well, so this is what I had to say. So in general, datasets are getting more and more complex, and data-driven approaches are becoming very important. In particular, contrastive learning is great when you have data that has significant biases, but it's important to know your data in order to transform accordingly. And well, this leaves the doors open for a bunch of applications that I talked about, and well, we use this to capture the spatially resolved properties of galaxies in order to trace their assembly history.
Okay. Thanks a lot, Regina. I'm sure we'll have plenty of questions for this talk, which highlights particularly the idea of potential of machine learning. There's lots of possibilities. So I have a first one from Paco on Slack. So what happens if you initially train your contrastive learning model using a smaller latent space dimensionality? You use 1024. Have you tried different values here?
Yes. So this SimSTLR model comes from Chen. It's a paper that was at the beginning. And they did the test and see what works better, if a small latent space or a bigger, and always bigger works better. Also, we tried it, and it actually works better. Okay. Yeah. Okay.
So and there is a follow-up by Paco, which I think is the question everybody is asking itself. Can you use your latent space as a generative model to generate new fake images?
No, in principle, no. That would be something additional that you would have to do.
Okay.
The problem, yeah, I mean, because we're not generating at the end is why we can avoid the biases that we have in the data, basically.
Okay, interesting. Question from the Irania. Oh.
Hi, thanks for a very nice talk. So my question is about the relation between the PCA analysis and the later machine learning part. So I assume the PCA was, grabbing out the linear correlations, right? So did you then try to connect the PCA components to some of your latent space clustering that you found? And were they the most prominent aspects of the clustering in the...
You mean applying PCA to the representations?
Yeah, what's the connection between the PCA components and the representations that you found? Presumably, they actually have captured some of the most prominent relationships at the linear level.
So yeah, I didn't apply PCA to the representation space. That's something that could be done. Yeah, definitely.
Okay.
Okay, we have a question here. And while the mic is moving, I have a follow-up question by Carolina Cuesta, which is actually a question everybody is asking for all of the talks here. How do you evaluate that it works better?
Than PCA, for example? Yeah, for sure. I mean, if you try to do the clusters with PCA, then you get divisions that are basically depending on the IFU size of the images.
Okay, that's an easy one then. A question here.
Hi. Regarding your cluster, did you try other methods? Because k-means is not ideal when your clusters are overlapping, and you have to predefine how many clusters you expect, right?
Yes, so two things then.
Well, it's k-means. Have you explored something else again?
Yeah, we tried hierarchical clustering, but the thing is that, and we also did several runs, so it's all explained. Where do I start? Okay, let's go first to the number of clusters, and then it will become more easier to explain the other thing. So for the number of clusters, what we did is we required that the clusters were independent from random initializations. So we did we run independent times this code, and we obtained, I mean, the space that you generate is not exactly the same because it's unsupervised, so you can't really generate the same exact thing. So the idea is that at least the distances between the galaxies should somehow be similar, right? So, okay, I'm entering into a mud here. So the idea is that if you run it multiple times and you divide the clusters should be similar from one to the other, right? So to define that, we asked that the clusters had 85% of the same galaxies, let's say. So that's how we define the clusters on one hand. And also when you do hierarchical clustering, because the distances are not exactly the same in each representation space in every run, that makes the division less accurate. So even k-means clustering that is super standard and gives you very different results in each run, it's still better than the hierarchical clustering in this case. Okay.
Okay, and I have a few other questions on Slack. So Mike Worm says great work, indeed. And he has a question I think is very generic. Do you find any physical parameters that don't connect to the contrastive representation?
Sorry, again?
So are there any physical parameters that do not connect with your representation?
Well, we did only look at physical parameters that were obtained or could be obtained from the maps that we were using. Surely if you use another one.
So you optimize for those parameters and you've not tried not using one of the parameters and testing whether it still is well represented, even if it was not in the
I mean, yeah, it
part.
could definitely be good correlating well with other parameters. We didn't try it. We just wanted to see if what we were getting made sense for the maps that we were using.
Okay. There are a few other questions. Perhaps some more from the room. No. So I think that last one from the room, and then everybody wants some refreshment, and you'll have a few other questions on Slack that you can answer at your convenience.
Hi, I was wondering why you decided...
Please, can you state your name?
Oh, it's Mike Smith. Yep. I was wondering why you decided on using SimCLR instead of a different contrastive learning model.
Because it was the one that was available at the time when I started, basically.
Okay. Yeah.
So then others appeared, but they were in PyTorch, and then I was using TensorFlow already, and because of the change, but that's basically...
Okay, cool.
So I think we'll stop here for this session. I want to thank all of the speakers of this session for keeping time and excellent talks, so thank you.